The Redskins are real reason I'm here. Okay. All right. All right, let's try another one. Let's try problem set 11.7 on page 1042. And let's do number 4, 6, and 8. It's gonna be another chart, like I bet.
Yeah, a big chart.
A big chart. So what do you want to know, Josh?
You want the bucket? I sure will.
Okay.
That's a big chart.
All right. They're talking about this chart, this marital status of the United States population ages 18 or older in millions. Okay, number 4, say if one person is randomly selected from the population described in the table, find the probability to the nearest hundredth that the person is a male. All right. So, what's the probability that you got a male if you take one person out of the population?
So if you have 212.5 total is your observed occurrences, and you have 102.4 events.
There you go, in millions.
48.2%.
So, does everybody see where we're getting those from? There's 102.4 million males out of 212.5 million people. So, probability that you pick a male out of all the people is
102.4
2.4
divided by 212.5.
212.5. So,
48.
probability of male. And what is it, 40?
48.2.
48.2%. So it probably came out to be 0.482, but we changed it. We can seamlessly go from decimals to percents in this class. Okay. That means there's more women than men, right?
Yes.
Yeah. All right. How about number 6?
Is a widowed female.
It's a widowed female. So what's going to be the sample space? Or I shouldn't say sample space. That's for theoretical. What's going to be the total number of observed occurrences?
212.5.
212.5, because you're not picking just from the women, you're just picking from everybody, right?
Okay.
So still 212.5 on the bottom.
Divided by 11.3.
Divided by 11.3, because you go widowed female, 11.3. So I'm just gonna population widowed female, 11.3 or 212.5. And what do we get?
Very tiny.
5.3%.
5.3%. I guess you don't die if you get married. And how about, what's the next one? Number
Among those who are divorced, find the probability of selecting a man.
Yep, number 8. Among those who are divorced, find the probability of selecting a man.
So you have 21.7 total divorced, and 9 are men.
Yep, because they're going among those who are divorced for women and men. So among those who are divorced, find the probability of selecting a man.
75% probably.
Yeah, so 9.0 divorced males over 21.7 divorced
That's not
ages. Should be about 47, 48%, right?
Sure, you would say.
41.41.
41%.
41.47.
You guys get the gist. What you have to do is figure out what occurrence, what event they're looking for, and you have to. To me, the harder part is figuring out what the total number of observed events is. So events are the total number of observed events. But the empirical probability is always going to be they're going to give you a whole bunch of data.
58%.
It wasn't 58%.
41. That was the one.
It has to be. It's because it's less than half. 50% is half, right?
I did the same thing. That's
Oh,
one for
for male.
female.
I did a female.
All right. So now let's talk about theoretical probability. I use one more.
Yeah.
Theoretical probability different than empirical probability. In theoretical probability, we're going to take the number of outcomes of an event over the number of outcomes in the sample space. The sample space, theoretical probability, the reason why they call it theoretical probability, because we have what's called a sample space. And the sample space is all known outcomes. And they like to use, like, tossing a coin, rolling dice. Right? See, normally in my handout we talk about the dice when you get it, so everybody always likes rolling dice. The sample space is all known outcomes. So say I have 2 dice, right? One dice that I get a 1, a 2, a 3, a 4, 5, or 6. And the other dice I can get a 1, a 2, 3, a 4, 5, or 6. So, from rolling these dice, I know what all the outcomes could be, right? All the possible outcomes. I could either get 2, right? If I roll a 1 and a 1, right? Or if I roll a 1 and a 2,
Same.
that's a 3. If I roll a 1 and a 3, it's 4. A 1 and a 4 is 5, 6, 7. If I roll a 2 and a 1, it's 2. 2 and 2 is 4, 5, 6, 7, 8.
2 and 1 is 2?
Yeah,
Huh?
2 and 1 is
2 and 1 is
3.
not 2, you're as bad as me.
See if you guys pay attention. It's supposed to, and as you can see, there's going to be a pattern, right?
It goes 4, 5,
So
6, 7,
4, 5, 6, 7, 8, 9, 5, 6, 7, 8, 9, 10, 6, 7, 8, 9, 10, 11, 7, 8, 9,
Getting worse when you get lower.
10, 11, and 12. Okay. So here's all known outcomes. How many outcomes is that?
36.
36. How do you know? Because it's 6 times 6. I once got an argument with a student in here. We had, everybody had the handout, and he has it on there, right? And I was like, saying, there's 36 outcomes. And he was like, how do you know there's 36 outcomes? And I was like, we counted them. And then, we're going through class and stuff like that. He's like, how do you know there's 36 outcomes? I'm like, we counted them. And he's like, you didn't count them. I'm like, well, I didn't have to count them because I knew 6 times 6 is 36. And then we get going on in class. He's like, I still don't understand why it's 36 outcomes. And I was like, what is wrong with you?
Look at your chart.
I was like, count them and you'll see there's 36. But anyway, it just made me think. All right, so it's 36 outcomes, right?
How do you know?
Believe me, there's 36 outcomes. The black outcomes, the blue is just the dice, but the black outcomes, those are 36 different outcomes if you're rolling 2 fair dice. Okay. Now, so these are 36 outcomes. So what if I say, what's the probability, the theoretical probability of rolling a 2? How many occurrences of a 2 do you see on there?
1 out of 36.
Yeah, 1 out of 36.
1 divided by 36.
Probability of 2 is 1 divided by 36. So it's the number of occurrences over
Number of
the
counts.
total sample space, right? Now, what if I say, hey,
Wait a minute,
what's probability?
you have 2 dice though.
Doesn't matter, you can only get a 2 one way.
Which one has 1?
You can only roll snake eyes.
You can only write
Yeah,
snake
yeah,
eyes one way,
oh,
you can only write
No
one
dice,
way.
no dice, no dice has a blank.
Got it, got it.
Okay,
We
now,
gotta take
got
it.
what's the probability of rolling a
You
6?
have a glass one.
See, yeah, 1,
It'd
2,
be
3,
5 out of-
4.
I always tell people,
36.
look at the diagonal on here. 1, 2, 3, 4, 5, 5, right?
5 out of 6.
So 5 out of 36, right? 5 out of
The best you got is 7, which is a
Yes.
6 out of 36.
Yeah, best you got a probability of 6. Probability of 7 is
6 out of
6 out of 36.
Which is
or
1/6.
1/6 or whatever this is. So hey,
Not a very good odds.
not very good odds, but if you play craps,
That's good house odds.
7's good, right? 7 is
Depends.
the highest odds, right?
Depends.
7 is the highest odds.
Only on the first row.
You're only on the first roll. So if the point is 6, then hey, you want to roll, right?
Or any other number besides 7 or 11.
Yeah.
Or 12.
You don't, you're not out on a 12.
Oh, yeah, it is 7-11, but it's hard to get a 20.
Hard to get two.
Low probability for a 12.
Yep.
Snake eyes, low probability. So, that's theoretical probability. Also, if you're flipping a coin, right? What's the sample space if you're flipping a coin?
How many times you throw it up and down?
No, sample space is you can either get heads or you can get
Tails.
tails. So that's the sample space. So what's my probability of getting heads?
1 out of 2.
1 out of 2, right? Probability of heads equals 1 out of 2 or
Half.
0.5 or 50%.
Same as the other one.
Probability of getting tails, same thing. Okay, so that's theoretical probability.
How about landing on the edge?
The probability of that happening,
Landing on
but
the
landing
edge.
on its edge and staying there.
Zilch.
Zero.
I ain't never seen
I
that.
would never say
I've
that.
never seen that happen. Have you?
Well, it could happen. Anything is possible.
Can you stand up going up on its edge?
Yep.
You can stand it on its edge, but
It's actually a
But
big
it-
argument.
Only that guy that can balance everything.
It's a big argument because that's not counted.
I don't have a
mean,
coin, so I
it's
can't.
Still a
can't even
possibility.
try it.
Okay,
Well, not probability.
Would you believe me?
Equals are great for that.
if I said all these probabilities add up to 1.
Yes.
They all add up to 1. Because if the probability is 1, then it's certain, right? Probability that I'm gonna walk back to that podium right now is 1. Because it's certain.
No matter
If
how
the
many
probability is 1, it's certain. It's always going to be less than 1, the probability, unless it's certain. It has to be certain. So that means, hey, if you add up, if like, what do we say? It's 1/6. The probability of getting a 7 is
I mean,
1/6.
2,
Probability of
3,
getting
6, 4,
6 is 5 over 36. If you add up all those probabilities, they have to add to 1 because they have to add up to 1 certainty. Hey, this you're getting it. So if you add up all the different probabilities, so if something's really probable, something next to it probably less probable, but not because the probabilities always got to add up to 1 theoretical probability. You can do this with cards too. Like, what is the probability of me pulling a 7 hearts out of the deck?
1 out of 52.
Well,
Unless
out of
you count
52,
jokers.
there's only 1 7 hearts. What about probability of pulling a 7?
4
out of
4 out of 52.
4 out of 52 because it's 4 sevens, right? What about the probability of pulling a club out of the deck?
13 out of 52.
13 out of 52. Everybody see where we're going with this? Anybody confused?
How about with dominoes? If you had a blank 5,
I don't know.
1 out of
28.
36.
I don't know. I don't know how to play dominoes.
28.
so I had
28.
You know,
You're
like-
playing those sixes.
You know why I don't know how to play dominoes? Okay, like I said, I went to military school. I could play all of that stuff that when you ain't got nothing to do, you're sitting in a room, I played. Every card game, every stuff like that. And it seemed like all the guys from the South played dominoes.
Yeah.
Well, you have,
And they'd be like, you don't know how to play dominoes? They'd be like, and so they come on, they were making fun of me. So I was like, no, I don't want to learn. So the whole time I was in college, I was like, I don't want to learn. So I never learned how to. So
But
whenever somebody
dominoes-
said, I'm going to teach you how to play dominoes, I was like,
change,
no,
you gotta change your
I don't
chart.
want to play.
You gotta change your chart. Dominoes, the difference between dice and dominoes is 0 counts. It was 0, 0 on each end. So you would have 7 times 7, 49 possibilities. And if you're asking for 1, it'd be 1 out of 49. Because 0, 5 could only happen 1 time.
I still don't want to learn about dominoes.
I'm just giving you the probability of the
play it
equation.
sometimes.
But look, and okay, my wife likes playing spades. So like whenever we go to one of her friends, she has a friend. You know how like you always have a friend that has parties all the time.
And
They always want to play spades, and she's like, "Come on, play spades." And I was like, "No." I said, "You know what? I played probably years of spades.
And service you bet.
I love
Yeah,
playing spades.
years of spades."
You probably lived
That's
on
just